There is a construction site somewhere in the world right now where the ground beneath the foundations is loose sand. Not bedrock, not compacted soil, sand. The kind that shifts, the kind that liquefies in an earthquake, the kind that has swallowed seawalls whole. For 100 years, the answer to that problem was cement. Inject it into the ground, let it harden, stabilize the sand from within. It works. It also costs millions of dollars per mile, contaminates groundwater, and requires the same industrial system responsible for 8% of the world's carbon emissions to produce. There is another answer. You run electricity through the sand, and the sand becomes stone, a process that could protect every eroding coastline on Earth right now and eventually replace the most destructive building material ever invented. Not slowly, not with heat, not with cement. A mild electrical current, too weak to feel, passes through sand saturated with seawater. And almost instantaneously, minerals begin to grow between the grains, crystal by crystal. Contact by contact, loose sand that poured freely through your fingers becomes solid, load-bearing rock. The Great Barrier Reef does this. Oysters do this. The White Cliffs of Dover, 110 metres of solid chalk rising from the English Channel, were built this way, grain by marine organisms that had no factory, no kiln, and no plan. Just chemistry and electricity. The question is why it took us this long to figure out how to do it on purpose. To understand why that question matters, you have to understand what cement costs the planet. Concrete is the most used construction material in human history. Every bridge, dam, hospital, school, apartment tower, and highway. The modern world is made of it. And at the centre of concrete is cement, the binding agent that holds everything together. Making cement requires heating limestone to approximately 1,450 degrees Celsius in massive rotating kilns. Those kilns run continuously on every continent around the clock. And they release carbon dioxide through two separate mechanisms. The first is the fuel, the second is the limestone itself. When you heat calcium carbonate to that temperature, it breaks apart chemically and releases carbon dioxide regardless of what fuel you used. There is no clean way to run the kiln. The carbon is in the reaction. The result is that cement production alone is responsible for approximately 8% of global carbon dioxide emissions. More than aviation, more than shipping. And unlike those industries, cement has no obvious clean alternative. You cannot electrify a cement kiln the way you can electrify a car. The carbon dioxide is baked into the chemistry. Which is why a civil engineer at Northwestern University named Alessandro Rotta-Lauria has been running electricity through tanks of sand. Rotta-Lauria grew up in Italy, surrounded by old buildings, Roman arches, medieval cathedrals, and bridges that have stood for 2,000 years. He became obsessed with a question most people never think to ask. What are those things actually made of? The answer in almost every case is calcium carbonate, the Colosseum, the Parthenon, the coral reefs of the Pacific. Limestone, marble, travertine, different names for the same mineral, formed by the same basic chemistry for hundreds of millions of years. When Rotta-Lauria started his lab at Northwestern, which he named with some irony soil, he began working on a problem sitting in the engineering literature since the 1980s. Researchers had known for decades that running electricity through water causes dissolved minerals to crystallize. Documented, understood. But no one had systematically asked what it could do to sand. Rotta-Lauria asked. The experiment he ran is simpler than it sounds. Take sand, saturate it with seawater, ordinary seawater, the kind that exists in unlimited quantities along every coastline on Earth. Insert electrodes, apply a low electrical current. The current changes the local chemistry around the electrodes, raising the pH of the water. That pH shift causes the minerals that are naturally dissolved in seawater, calcium, magnesium, and bicarbonate to stop being dissolved and start being solid. They precipitate, they crystallize. And because sand grains are present, those crystals form in the spaces between them. Each crystal bridges one grain to another, then thousands, then millions. The minerals grow around and between the grains like natural mortar, except the mortar isn't mixed and applied from outside. It grows from within. In laboratory experiments at Northwestern, a mild electrical current instantaneously transformed marine sand into a rock-like, immovable solid. The same minerals that built seashells and coral reefs formed between individual grains of beach sand. Loose sand became stone. No heat, no cement, no carbon dioxide, just electricity, seawater, and time. There is one detail about this process that stops people when they hear it. It is reversible. If you switch the anode and cathode and swap which electrode is positive and which is negative, the electrical field reverses. The local pH drops instead of rising. The minerals that had crystallized between the sand grains begin to dissolve. The stone becomes sand again. The same switch that turns sand into stone can turn stone back into sand on demand. This is not a theoretical curiosity, it has direct practical implications. Coastal communities could harden stretches of beach or seafloor against erosion and storm surge, then reverse the process if the coastline changes. Construction sites could stabilize loose ground for foundation work, then allow it to return to its natural state once complete. No permanent chemical change, no contamination, no residue, just a change of polarity. The applications that Rotaloria's team has outlined go well beyond the laboratory. Over 40% of the world's population lives in coastal areas. Erosion is accelerating. Seawalls, which cost millions of dollars per mile and require massive stone foundations, are being swallowed by the very ground they are meant to protect. The sand beneath them liquefies under repeated wave action and the walls sink. Electrochemical sand solidification offers a different model entirely. Instead of building a wall on top of the sand, you harden the sand itself. No imported materials, no heavy equipment, electrodes installed in the seabed, low current applied. The coastline stabilizes from within. At an estimated cost of $3 to $6 per cubic meter, compared to $70 or more for conventional chemical stabilization, the economics are as compelling as the engineering. Rotaloria estimates the treated sand should maintain its durability for decades, protecting coastlines and property against erosion and sea level rise. Because the voltage involved is too mild to feel, there is no hazard to marine life. Other researchers have used similar low voltage processes to restore coral reefs. The chemistry is the same, the marine organisms are unaffected, but hardening beaches and coastlines is actually the small-scale application. The real target is the $300 billion concrete industry, and that is where this technology gets genuinely disruptive. Working with Cemex, one of the largest cement producers in the world, Rotaloria has been exploring whether the same electrochemical mineralization process can be used to grow construction aggregate from seawater, not to stabilize sand in the ground, but to manufacture new mineral material for concrete production itself. The vision is specific. Most major cement plants are located on coastlines. They are there because limestone is heavy and ships easily. Those same plants sit next to an unlimited supply of seawater. Rotaloria's proposal is to install modular electrochemical reactors at those coastal plants. The plant produces cement and carbon dioxide. That carbon dioxide gets captured and fed into the reactors. Seawater feeds the reactors, renewable electricity runs the current, and the reactors grow mineral aggregate, calcium carbonate, that can replace mined limestone in the plant's own concrete production. The same plant that was emitting carbon dioxide becomes a plant that sequesters it, locked inside the material it sells. He calls it circularity. The carbon dioxide goes in, the stone comes out, nothing goes up the stack. But there is one more output from this process that nobody talks about. When you split water with electricity, a second reaction happens at the other electrode. Hydrogen gas is released. Clean hydrogen is the same fuel that governments and energy companies are spending hundreds of billions of dollars to produce at scale. It can power vehicles, heat buildings, and store renewable energy without producing a single gram of carbon dioxide. Rotaloria's process produces it as a byproduct, not as the goal, as the side effect. One process, 3 valuable outputs: carbon-negative aggregate, clean hydrogen fuel, and a cement plant that sequesters carbon dioxide instead of emitting it. The facility that was a liability becomes a resource. There are real obstacles between where this technology is and where it needs to be. The first is scale. Electrochemically solidifying a stretch of beach or a foundation site is achievable with current technology. Producing enough mineral aggregate to meaningfully reduce the world's 4 billion tons of concrete each year is a decades-long project. As of early 2025, the core research has been peer-reviewed and published. The CEMEX collaboration is active, the material works. What comes next is the hard part: optimization, pilot projects, and the slow accumulation of the performance data that industries require before they change. The second is the carbon dioxide source. The carbon-negative aggregate process works fastest when carbon dioxide concentration is high, ideally sourced directly from an industrial emitter. The atmosphere contains roughly 0.04% carbon dioxide. A cement plant exhaust stack contains between 14 and 30%, that is 300 to 700 times more concentrated. The process works at atmospheric levels. It works far faster at the source of the problem. The third is building codes. There are no structural standards for electrochemically treated sand or grown mineral aggregate in any jurisdiction on Earth. Before an engineer can specify either in a real project, it has to be tested for strength, durability, fire resistance, and freeze-thaw cycles. That data has to be assembled, committees review it, standards bodies adopt it. Cross-laminated timber was developed in Austria in the 1990s and did not appear in the International Building Code until 2015. 20 years of testing. 20 years of committee meetings, 20 years during which the technology existed and most of the industry could not use it. Electrochemically treated materials will face the same timeline. This is not obstruction. It is the system working exactly as it was designed to, because buildings fall down when materials fail. But the climate does not operate on a committee timeline. 8% of global emissions is not and was a problem that can wait for the next standards revision cycle. What Rottaloria grew up looking at in Italy, the arches, the cathedrals, the bridges standing for 2,000 years, was always calcium carbonate. The same mineral that oysters grow, the same mineral that coral reefs build, the same mineral that the ocean has been depositing grain by grain without a factory or a kiln for 500 million years. He found a way to grow it in hours, not in a kiln, not in a factory, in the ground, in the sand, with electricity. The science works, the coastal erosion application is proven in the laboratory. The construction aggregate research is active and funded. The CEMEX partnership is real. The chemistry is solved. The material exists. The process is understood. The only question left is speed in the sand with electricity. In